guys can feel free to move up. I have red hair, but I'm not dangerous. Okay, yeah, I am Charles Haupert. I'm from A2S. I'm an electrical engineer. I've been doing water, wastewater, primarily projects on the electrical side for probably the past 5 years. A lot of controls, a lot of power, so I come across a lot of things that I see in the field that have been done that maybe I personally wouldn't do because it would end up being an issue later that I wouldn't want to deal with, or something like that. So today we're going to talk a little bit about, first we're going to start off with theory in case you don't really know what a VFD is. Kind of talk about how internally they work, so you have a better feel and understanding for why we do some of the things that we do as a consultant. And then we'll go into applications of where it makes sense to use VFDs. And then also show you some of the benefits, cost savings, and other items that VFDs are useful for. But then also I'm going to talk about concerns and things that, you know, if you're going to install a VFD in an application that currently is not on a VFD, things to watch out for so you don't have problems after you make that switch. And then lastly, we're going to talk about how to troubleshoot on a high end if you're having problems on your VFD. And high end meaning I'm not going to go into any specific drives like a Square D or an Eaton, but more what to look for and how to approach a problem if a problem occurs. So with that, before we talk about VFDs, let's talk about a starter. Hopefully everyone here that works on pump stations, lift stations, wells, distribution, water plant, wastewater plant, has motors, because if you don't, you're not moving water in most cases. And the way it's been done in the past, and the way we continue to do it, depending on the situation, is an across-the-line starter. And what a starter does is, there's basically a contactor or a relay that a low voltage is applied to it, and it pulls in these contactors here that are rated at the amperage or whatever of the motor, closing those and applying full line voltage across the motor at 60 hertz. In the US, all of our power is 60 hertz, whether it's 120, 240, 208, 480 volt. We're always at 60 hertz. That's constant. That doesn't change. The voltage is what changed. And in my field, a lot of times it's 120, 240, 120, 208, or 277, 480. I do get into some bigger stuff, but not very often. So this presentation is kind of in that voltage range and what it applies to. So here's our little sine wave. This is one phase of a three-phase service at 60 hertz. Voltage doesn't matter. And what a variable frequency drive is going to do, it's going to control the speed of your motor by controlling the frequency of the AC power supply. So what we want to do is we want to change the speed of this signal. How do we do that? With this equation. By changing the cycles per second or the frequency going into the motor, we're varying the motor RPMs. The RPMs of the motor are equal to 120 times the supply frequency divided by the number of poles of a motor. So if we're running a motor across the line and it's a 4-pole motor, we have 120 times the frequency, which is 60 hertz, divided by 4, which is an 1800 RPM motor. To slow that down, the only thing that we can change is F, our supply frequency. Which this slide says. I wanted to just show this slide. I actually took this yesterday with my fancy BlackBerry that might ring because when it's off, it's not off sometimes. But this was on the showroom floor, and what it was is Schneider Electric, they had like this little VFD and an enclosure, so I just wanted to kind of go through the components, if you can see them way in the back there. On the right here, there's a main circuit breaker within this enclosure. And from that, it looks to me, and I have a hard time following the wiring. I was looking at this morning, following the wiring on this photo. But it looks like down here, they must have like a bypass contactor. So if they want to run this across the line, if the VFD failed for some reason, they could. Over here on the right is a control power transformer. What that does is it's going to step down your 480 volt down to 120 for the controls. From here, it looks like it runs over to this VFD. This is the VFD itself. This is the device that has all the brains that, when we have problems, that little display on the front might give you an error code. Control terminal blocks down here to distribute that 120 volt power and controls and things like that. Condensation heater. And then down at the bottom, I don't know if this is I can't tell if this is on the input or output side. This is either an input line reactor, which is a device that's used to oppose rapid changes in current, so it should protect your VFD and reduce harmonics. We'll get into that in a little bit. Or it's an output filter, otherwise known as a DVD-T filter for if a motor is a long ways away. So I'll talk a little bit more about that a little later in this. So we're going to zoom in and schematically, I guess, into this box, the VFD itself. And this is what it looks like. Power comes in. The VFD itself is going to take that AC three-phase signal, and it's going to convert it to a DC signal. Once we have it converted to DC, then the device is actually going to output it, modulating it into a three-phase AC signal that can vary the frequency, but it looks kind of weird. And down here, it's kind of showing it, but this next slide, I think, shows it better. So the darker line represents a typical AC sine wave, and the rectangular waves are the pulse width modulated output of the VFD. It's a DC voltage, so that's always constant, and so the voltage is always the same height. The amplitude is constant over the entire frequency range. Basically, the lower resultant voltage at the motor is done by shorter pulses. So the width of the pulse is actually used to determine the actual output voltage seen by the motor. And I'll show you another slide here in a second that describes that. And then the off time is actually the supplied frequency from the drive. So by adjusting that off time of these pulses, we can change the speed of the VFD, and this is all done internally into the drive with what it's created to do. But it's kind of interesting. And then these little fast switches you see is actually all these IGBTs, which are insulated gate bipolar transistors. Doesn't matter, but they switch really fast. And what you guys might run into is a motor that whines or makes noise, and you feel like you or some supplier or someone has to come out and adjust the carrier frequency of the VFD. And that carrier frequency is actually this really fast switching that's happening on the output side. So the higher the carrier frequency, which typically is between 8 and 16 kilohertz, the more losses you have. So if you have a VFD with a high carrier frequency, you might not hear it, but it's probably going to be putting off more heat, and your VFD may not last as long. So ideally, if you can keep that lower without creating a whine or a hum on your system, that's a good thing. So from this, what's it look like at the motor? Because this is showing the modulation, but what are we sending to the motor from our VFD? We're sending something that looks like this. The voltage is all constant, and the width of the pulses are different. And what that's doing is mimicking an AC sine wave using a DC voltage. But because of the properties of the motor, what the motor actually sees for current is this nice shaped sine wave, which is why they work. Doesn't hurt your motor at all, assuming your motor is rated for VFD use. But The motor actually acts as a filter, and these pulses, it filters these pulses into a smooth, somewhat smooth sine wave. And I say somewhat because all these little jagged edges here are something that, as an engineer, we have to deal with, or they might create problems on your system elsewhere. So that's kind of a summary of the theory of what a VFD is doing and why we're going to see some of these concerns and benefits from that. So what can we do with a VFD? We can use it to optimize a process through speed control. Basically, we can slow down our motor from 1800 RPMs down to a slower speed. VFDs have high power factor. Because we're doing this AC to DC back to a modulated AC conversion, we have almost unity power factor. A motor has a power factor of 0.7, 0.8, 0.85, somewhere in there. And what that basically means is it has a certain ratio of real power to reactive power, or reactive power is also known as imaginary power. And the utility company doesn't like to supply imaginary power because they still have to generate it even though it doesn't really do anything. So VFDs have an advantage from that perspective. They optimize motor starting characteristics. We can ramp up the full speed quickly by drawing 100 to 150% full load amps. If we're starting a motor across the line, we're over 200%. And if we're starting a really big motor across the line, when we have that high amp draw, what happens is the utility can't keep that voltage up. Your voltage will drop on your system, and you might have your lights go out, you might have problems on your system that way starting across the line. So a VFD and a soft start eliminate that. I'm going to talk a little bit about soft starts here. A soft start is basically has the ramp functions of a VFD without the speed modulation once we're up to full speed. So nowadays, with VFDs being as common, I guess, as they are, I rarely find myself putting in soft starts unless it's an application for a motor that is always going to run full speed all the time. If there's ever a situation where it might not run full speed all the time, we typically will just put in a VFD, because then that option is available. VFDs can take any form of input, and what that means is we can power a three-phase motor on a single-phase VFD, which is pretty cool. And there's certain situations, especially I run into at like remote lift stations or well houses, where we want to modulate the speed of a motor, and also we don't have three-phase in the area, and a VFD is a perfect application for that, replacing older technologies like out-of-phase. So for speed control, what can we do? So we have power coming in, it hits your VFD powers your motor, and that runs a pump. Well, if we have a pressure or flow transmitter on the line, flow meter, magnetic flow meter, or pressure transmitter, we can run that 4 to 20 milliamp signal back into our VFD, and through SCADA or some other external setting, we can provide a pressure and flow setting on the drive and match that. So we can keep a constant pressure, constant flow on the system that might be less than running that motor full speed. Some advantages. Using a VFD reduces mechanical stress, which, if we can reduce leakage and mechanical stress, and water leakage in the distribution system is proportional to the pressure maintained on the system. So if we don't need to maintain a really high pressure all the time, we can reduce that pressure, hopefully reducing leaks, reducing stress. If we reduce the stress on anything, it should increase equipment life. We're going to eliminate or reduce water hammer, which we don't like water hammer. And using a VFD to do that by ramping up slowly is a perfect application for that, especially on a big pump. And we can also get rid of some equipment. There's a lot of situations where you see a throttling valve or damper installed to create like an artificial head because they want to reduce the amount of flow from a motor that started across the line. Well, now we can get rid of these throttling valves, put a VFD in, run it at a reduced speed if needed, and not have to go out and close a valve some to throttle down due to high turbidity on your river or whatever it might be. So, and here we're showing a little chart, throttling valve and using a VFD. When you're using a throttling valve, you're still running the same amount of power to the motor at full speed or 60 hertz, full load amps. So you're still spending that much money on energy, where with a VFD you are actually throttling back your energy. You're not just creating a restriction in the pipe. So it does add up to energy savings and cost savings. Avoid power factor penalties. This is a representation of the power triangle, and it's one of those things that if you're an electrical guy, you see and you deal with in school all the time. But on the x-axis here, that's real power. Real power is in kW. That's what XL Energy or Great River Energy bills you for on your system. Reactive power, that's the imaginary power part. That's what the utility companies don't like you to have very much of, because they need to supply that. They need to supply kVA. That's basically the combined vector sum of these two. They need to supply kVA to you, and so a lot of times you'll see utilities have a power factor penalty if your power factor is below 0.9. And so the thought is, what we want to do is we want to get this kVA line on top of that kW line, which basically means we don't have any reactive power. And using a VFD is a great way to do that, because a motor is 0.7, so that angle is a little bit bigger. And if we get that angle down to 0, then what this is saying is the cosine of 0 is 1, so 1.0 power factor. But using a VFD is a great way to improve your power factor in your plant if currently you're getting dinged on power factor charges, because a VFD has basically unity power factor. Before I move into this, one more thing on speed control. Speed control, this is going to be an example of using speed control to save energy. And basically, it's a payback analysis for using a VFD on a centrifugal blower. One thing that you do have to kind of be wary of if you're like, oh, hey, I want to put everything on VFDs, it'll be awesome, is if you have a pump curve that's a sharp bell shape and doesn't have a nice flat top, you'll lose. If you move too far either way on a pump curve, a lot of times, a good example of this would be a vertical turbine with a deep well. You might, by turning that down, you might not get the cost savings you're looking for, because you move so far on that pump curve that your efficiency goes in the toilet and all your energy savings is negated by inefficiency in your pumps. So just be aware of that. This is a great example of where that, oh, I'm not there yet. I'm going to jump ahead. Okay, let's talk about energy savings. I'll be there on the next slide. Number one, the pump affinity law. Power is proportional to the cube of the shaft speed. What that means is if we slow this motor down, we're going to save a lot of money and energy. So we can use these VFDs to run centrifugal fans and blowers, or fans, pumps, and mechanical systems more efficiently. A lot of times a mechanical system that's run across the line has some sort of pulley system to reduce the speed of the fan. We can do that with a VFD and eliminate that system. And this can add up to a lot of money. And we all like money. So here's my example. This is a kind of a wastewater example, but we do get fairly big blowers and water plants and stuff too. Let's say we have a 200 horsepower centrifugal blower that needs to supply air 10 hours a day, 200 days a year. To run that blower at full speed, basically running it across the line, we're spending $23,872 a year, assuming we're paying 8 cents per kilowatt hour. So 200 horsepower, 0.746 kilowatts per horsepower, 2,000 hours, 8 cents, 23 grand. But what if we don't need to run this full speed for 200 days, 10 hours a day, 200 days a year? Let's say we need to only run at full speed 25% of the time, and the other 75% of the time, we only need to run it at 70% speed. So, we have 200 times 100% cubed, that's a pump affinity law right there, times the kW to horsepower, times the hours, times the kilowatt hour rate, and then here, we're only running at 70%, so there's your cube rate. It's really hard to keep this still. And so now to operate this same blower on a VFD, we're only spending we're only spending $12,109, essentially saving $11,763 per year. This VFD in an application where we don't have a pump curve and we're not losing any efficiency by slowing it down in this scenario, it'll pay for itself in 4 years, 3-4 years, I suppose, if the drive costs $30,000 to $40,000. So there's situations like that can lead up to a lot of savings over the life of the drive. As I mentioned earlier, we can use a VFD to convert single to three-phase. And this might be beneficial in locations where three-phase power isn't available. What they used to do, or what we see a lot of that, near end of life needs replacement, is something called an ATC. Nowadays, I haven't ran into a situation where I've wanted to install an ATC because I can use a VFD. The VFD must be derated for single phase installation, since a 7.5 horse VFD is rated for 7.5 horse three-phase. Now, if we're running single phase input into that VFD, it needs to be derated. So be aware, if you're doing a situation like this, suppliers should have charts showing the derating. I think a lot of times it's about 50% derated, so you'd be putting in a 15 horse VFD for a 7.5 horse motor. There are size limitations, about 50 horses as big as you can go. And normally if you have more than 50 horsepower load at a site, single phase the service size gets too big and not cost effective. But if you're in a remote location in the middle of nowhere and there's a single phase line nearby and no three phase, it may be way more cost effective than trying to get the utility company to extend three phase to the site. I've ran into some situations where I've gotten quotes to extend three phase to sites and they want to charge $250,000 to get three phase there, and it's like, no thank you, that's a lot of money. Concerns. So those are all the benefits. Now we're going to roll into some of the concerns of what VFDs, or concerns of using a VFD to make sure you don't run into issues. VFDs, because we're converting from AC to DC back to AC, there's heat losses in all these processes, and because we have that high switching speed, there's heat losses there, and we need to do something with that heat. This is my picture metaphor for a VFD outside in the sun in a lift station that runs a lot in the summertime. The enclosure has the sun on it, and it gets very hot inside the enclosure. If the VFD itself is running a lot, that's also producing heat, and they don't like heat. So make sure we confirm proper cooling and ventilation is present. Now, depending on the situation, how often it runs, the size of the drive, we're talking, air conditioners or fans or whatever. This is an MCC with a bunch of VFDs mounted in it. There's an intake louver here on the bottom. You can see there's like a little screen in it so we don't suck in dirt and dust and trace chemicals and stuff. And then there's a big fan right here on the front, as well as ventilation up above. Heat is a big enemy of VFDs, and a lot of times if I get a call from someone and their VFD isn't working. Oh, it keeps tripping out on overcurrent or whatever it might be. The first thing I ask is, are your fans working? Well, we don't have fans. Okay, can we open up the enclosure and put a box fan on it for now, especially if it's a critical situation and it needs to run. And sometimes that box fan has gotten people by until they get their new fans installed or the room cooled. VFDs, they create system harmonics, otherwise known as electrical distortion, that must be mitigated. The switching of the power electronics within the drive, combined with the distance to the motor, create this output voltage distortion waveform. It's a high frequency noise, and we have to do something with it. And there's several ways to handle that. This is my little picture of a distorted AC signal, and this is a nice, pretty clean one. And for some reason it's in 3D, because I found it on the internet. You can use an input line reactor, that's what this is. This goes ahead of the VFD, and it opposes rapid changes in current. Other things we can do, we can install 18 pulse VFDs. Most VFDs, the off-the-shelf little box that's normally about this big, if it's 20 horse or so, is a 6 pulse drive. 6 pulse drives up to 200 horsepower. Then you want to start looking at, well, instead of a 6 pulse drive, maybe we go to 18 pulse. And what an 18 pulse drive does is creates that many more pulses of that modulated signal to get that much more clean of an output to the motor. An 18 pulse drive nowadays inherently meets something called IEEE 519, which is less than 5% total harmonic distortion, which most utilities have a requirement within their connection standards that says that your plant must meet that at the point of common coupling, which essentially is at the secondary side of the transformer feeding whatever your power of the utility transformer. What else can we do? We can put on DC bus chokes. That's something that goes on the downstream side of the VFD. There's also something called a harmonic correction unit. Eaton makes one. It's called an HCU. And Square D makes one called an AccuSign. I think there's also some other ones out there from some of the smaller filter companies. And what that does is it actually monitors the harmonics and injects opposite negative current to counter that. It's an expensive box that does magic, and depending on how many VFDs you have in a plant, sometimes it makes more sense to have this device as opposed to a bunch of 18 pulse VFDs, because 18 pulse VFDs also cost more money. One other thing you can do is ahead of the VFD, instead of a line reactor like this, they make something called an input harmonic filter that is sized for, it's a filter that's sized for that specific size pump or motor or VFD that should also be IEEE 519. So noise is bad, we want to get rid of it, and that's why we do some of these things. I pulled this right off the Excel Energy Standards table. This is a harmonic current table showing kind of the total demand distortion based on your ratio of short circuit current to load current. A lot of times you're going to fall right in this area, 5%, 8%. And a VFD, without any of these fancy doodads that I'm talking about, has close to 30% harmonic distortion. So we need line reactors, we need to take these big loads and put them on 18 pulse VFDs and things to try and negate that. Now there's other loads within your plant that are not harmonic loads, such as unit heaters and loads of that nature that are linear. But normally they don't, that quantity or that ratio of linear load does not negate the amount of harmonics produced by VFDs, especially in a water, wastewater plant or small pump house, well house, and things like that. So be aware that this IEEE 519, a lot of times utilities may not enforce it, but that doesn't mean that you don't need to meet it. And I have been in situations where they do enforce it and they ask to see the design, and if we don't meet that standard, they will not let us turn on a new lift station or pump station. So if someone says, hey, you got a panel, I'm going to put some VFDs in there and they're this much and it's going to be great, just be aware of these harmonic issues. Another thing of concern is VFDs supplying motors. The motors and cable have to be insulated for overvoltage spikes caused by the VFD. Because of these electronic switching within the drive, on a 480 volt VFD, it's converted to the DC bus, which is 600 volts. I think 690, I believe, is pretty standard, is the DC voltage in those drives. And then output it to the motor, and because of this switching, it's not just a 90-degree switch. There's a little overshoot and undershoot voltage that you could have combined with the distance to the motor. It's called capacitive coupling. Voltage at your motor almost 1400 volts, which is why you see a lot of times an inverter duty rated motor rated at 1600 volts. So that's just a dielectric insulation property. Make sure your motors are VFD or inverter duty rated. And if they're not, then some things need to be done. There's things called motor terminators you can put at the motor that chop off that voltage spike. But nowadays, it's becoming a pretty common practice that new motors are inverter duty rated, especially they need to be if they're on a VFD. VFDs have distance limitations. You want to put your VFD as close as you possibly can to the motor. That's practical. Don't put it out next to an open basin with a lot of chlorine. Don't put it in a lime silo full of lime and dust. But there are distance limitations, and as we get further away from the drive, the motor gets further away from the drive, extra filters need to be added on the output side to make sure that motor is getting a clean signal. And about 1,000 feet is as far as you can go. Any further than that, you get so much voltage drop on your conductors anyways, you're wasting money. What else? Oh, they might put noise on other systems if your output conductor is not shielded properly, if things aren't grounded properly. You might install a new VFD, and now all of a sudden your flow meter is giving you bad readings. Why is that? It's inducing noise on the analog signal of your flow meter, or pressure transmitter, or AM radio, if you're listening to AM radio in the water plant, I guess. And also creates circulating currents within the motor that could cause bearing fluting. This is a picture down here of bearing fluting. I think I've ran into one situation where it showed up in my 5 years of doing this. So if it's a big piece of equipment, what do? We put an insulated bearing or a ceramic bearing on the non-drive end of the motor, and we put something called a grounding ring. Looks kind of like this. Gets mounted on the shaft of the motor. And what it does is there's these little conductive brushes here that pull extra circulating current away from your motor and to ground to keep it from having any fluting issues. VFD output conductors also should be either shielded cable or in rigid steel conduit that contains that noise produced on the cable from the output of the VFD. Don't run it in building wire in PVC conduit. That will greatly increase your chances of problems arising elsewhere on your control system, speaker system, whatever it might be. And that is most of the concerns. What are we doing for time here? So, maintaining it. Just some tips. Keep it clean, keep it dry. Check the connections and make sure they're tight. Obviously not while it's energized, but connections can come loose, and when they come loose, heat is generated. When heat is generated, products and devices fail. Thermal imaging can detect this, or routine maintenance. And then keep it cool. Make sure your fans are running. If they die, replace them. And yeah, keeping it clean. Don't replace the filters on the input side. And make sure your drive isn't getting dirty. It's just probably like your home computer or work computer too. All right, we're going to talk a little bit about troubleshooting. And the number one tip I have is don't troubleshoot the VFD. Troubleshoot the application. This is going to be kind of a high-level troubleshooting approach. but it might give you something to think about. So ask yourself, has there been any reasons for power quality concerns? Meaning, did a storm just go by? Did the lights go out for a second? Did the generator kick on? What happened that caused this VFD to fail? Back to cooling again. Is proper cooling present? Is it still working? Is the input side of my cooling clogged? Is the AC still working? What's it set at? Is it sized correctly? And you have to understand your load. Without a load, there's no reason for the drive in the motor. And what that's basically saying is, if I have a 40 horsepower drive on a 40 horsepower motor that's pushing against nothing, it's not going to draw 40 horse. It's going to draw like 5. Whatever it costs to overcome the moment of inertia within the motor. So your VFD isn't going to be pushing hard, and it's not going to be putting off as much heat if there's no load. Overcurrent faults are the most common fault that will shut down the drive. And overcurrent a lot of times is a cause of excess heat. So they go hand in hand. This is a little, oh hi, I forgot to go forward again. That's what I just said. Sorry about that. Here's a little acronym I found called SMARTS: Safety Manuals, Applications, Troubleshooting, Readings. Readings and troubleshooting. Safety is always your first concern. I do a lot of arc flash studies lately, and so I want to say anal about electrical safety. And make sure what you're doing is safe for you, it's safe for the people around you, and it's safe for the equipment. Manuals, every manufacturer has a manual, and they're all different. They all have different error codes. Their programming is different within the device. Setting them up is different. So without those manuals, it's really hard to troubleshoot what's wrong if your HMI or your display on your VFD is giving you an error code. So have those nearby and get those error codes and write them down, because they're going to help lead to the problem. Normally when a drive does shut down, it's not due to the drive. It's due to an external condition. So make sure you check the motor, you check the safety interlocks. What was going on when this happened? Did something get stuck in a clarifier basin? Is there a rag in my submersible pump in the wet well? All these things can cause to these issues that have nothing to do with the VFD. The VFD is going to shut itself off, probably to protect itself from burning itself off. And then again, like we talked about, using the manuals as a powerful diagnostic tool to troubleshoot an error code. Readings. If your display on your VFD has temperature readings, it makes sense to just log those once in a while, especially if it's, your motor runs pretty continuously, and trend it throughout the months or the years. And over time, if you start seeing a rise in temperature, that's going to be kind of a precursor to future problems. So you might be able to, proactively take care of that before there's a major issue and it fails. I want to talk a little bit more here about electrical safety. NFPA 70E is standards, electrical standards in the workplace. It's a very, very good book, and if you're an operator, if you're a superintendent, or if you're even doing stuff on equipment that might be energized, you should pick up a copy of this, because it talks about lockout tagout standards, it talks about PPE, it talks about different procedures on how to approach equipment that may or may not be energized. PPE, arc flash is a big deal. I know I said it once, if you know what arc flash is, but basically it's where instead of the electricity staying on the conductors, you get a fault that it's not a bolted fault, so it's not a fault from a conductor to a conductor or a bus to a bus. It's a fault through air, and when that electricity jumps through air, there is a high impedance medium, so it creates heat, and when it creates heat, it causes gas and copper to expand, melt, expand, turn into a vapor, and you get a really big explosion, which will kill you if you're not wearing the correct PPE. And you want to go home at the end of the day, you don't want to be like this mannequin. This is not a person, I'm not that mean. Like that would be a bad day if you're working in something energized and that happens to you. So be aware of arc flash and the dangers there, and a few more tips is just make sure you know what happened when you had a problem and document that. So if you need to call someone, you can explain to them what was going on when the problem failed. That helps consultants and suppliers a lot. If you say, well, the power went out and then the generator kicked on, and when the generator kicked on, the VFD didn't restart. Okay, well maybe it's a setting in the VFD or something like that that can be changed. Double check the protective interlock and safety relays. On a clarifier, normally you got high torque, and one of those is normally wired back to a relay that's wired into a disable bit of the drive, and it might need to be reset. Oh, it's not restarting from SCADA. Well, that's because you need to go to the VFD and physically hit the reset switch on the drive to open that relay, and then you can just restart your equipment. And develop systems to systematically troubleshoot the issue. That's in-house, but if you have a general standard of, first we go to the motor and see if that's okay, we shut off this, do this. It's all internal, it depends on your application. A lift station is obviously different than a 500 horsepower high service pump, but a system in place will help get stuff back online sooner. That's all I have for you today. I feel like I've been talking the entire time because I have, and I guess now I'll open up the floor for about 8 minutes of questions.
Any questions out there for Charles? Let me get you to the mic here. Mike will bring you the mic.
Can you talk about capacitor banks and their use in VF drives and why they fail?
Capacitor banks within drives. Yeah, there are capacitors within the VFD. First off, I'm gonna, across the line starting. Normally, if it's a big enough motor, you'll see power factor correction capacitors. Those are installed because motors have that low power factor. So when you have a VFD, you don't have power factor correction capacitors, but yet you still have capacitors within the drive. They fail because what happens is if a capacitor is sitting, if a VFD sits on a shelf for a long time, it is not energized, and if that capacitor is not energized, a lot of times what will happen is the insulation in those capacitors can get moisture, and when that happens, then you go to rehook it up, and your capacitors within the VFD fail. So in past situations where we've had issues of drives failing, it's because it was a drive that was either supplied by an electrician or supplier that happened to sit on their shelf for way too long. And so it got installed, it ran right at first, and then a year later died, and it was because it was an older drive that sat unused. So as far as if they're energized, so if your VFD is installed, it's energized, and it's due, there shouldn't be a lot of failures with the capacitors within the VFD. So I don't know if that helps or not.
Did it work for you?
I've had it happen a couple of different drives, and they've been drives that are used.
Have they been
in service?
They've been in service a while?
Yeah.
The only other thing I could see happening is you're getting like voltage spikes within into the drive that are over time damaging that VFD. So maybe a surge arrestor on the front end, or input line reactor for sure, to try and knock that down. But yeah, I mean the VFD sitting on shelves and then getting installed years later is where I see issues with the capacitors within the VFD have problems.
Another question, Ron? You haven't seen me move this fast, have you?
So what are your thoughts on preventive maintenance? Do we need to look at this yearly, every 5 years, only when it's broken? So what are your thoughts?
Within the VFD enclosure itself, because I mean the VFD is a box that's kind of, at least if, let me go back.
Well, I have a company that, and I've dealt with these people in the past, and they just called me again the other day and said, "Do you have any VFDs you'd like cleaned, looked at, inspected? And is it really a need, or is it should be something that should be done annually, or every 5 years, or depending upon the enclosure? But let's say it's in a panel, a lift station panel, or in a building, pretty clean atmosphere."
Yeah, I mean, if it's clean, you know, if it's clean, obviously you don't need to clean it. Probably what they're getting at is, you know, they're going to make sure that they replace the screens on the input side of, you know, I'm sure you have some sort of ventilation. So they're going to clean those screens or replace them or whatever. They're going to vacuum it out, make sure it's clean. They might take a thermal imager or a temperature sensor and shoot the terminals of the VFD to make sure your connections are tight. You know, they might take a look at how often to do it. It really depends on your situation. If it's a clean scenario, I think as long as you're aware that you need to make sure your fans are still working and then that the input side through the ventilation is clean and within the enclosure is clean, you know, periodically you want to look at it for sure. But how often, I guess, depends on the application where it's installed. I know my house gets dirty when I don't clean it in like a month, but it really depends on your plant. There's some plants that are just immaculately clean. They have a guy there all the time cleaning, and there's other plants you go in that are a little bit smaller, less staff, that maybe they don't have the time or the effort to get to that. So you get in some electrical rooms that are a little bit dirtier where you might want to, you know, it goes back to now you want to look at it more because it is a dirtier environment. But you know, hiring someone outside to come in and clean it, you could probably shut the upstream breaker off and do it yourself too.
Any other questions for Charles? Well, being the first speaker of the day and getting here through the snowstorm yesterday probably, so we give him a round of applause for showing up and doing a good job.